Okay, so everything happens in class is then here. Okay, so let's get started. Okay, so linear algebra. Okay, so anybody knows what linear algebra is? Any idea? So what is it a prerequisite for? So you're taking it, so it's supposed to bring you to some place, and that place is not calculus. So usually mathematics courses are taking either calculus or pre-calculus. So this isn't it. So anybody can tell me why you're taking it? Anyone? It is prerequisite for something. So your advisor told you to take it. So why you? So it did explain why. You don't have to raise your hand.
Gotcha. I know that it deals with matrices. Matrices is a big part of like computer science stuff.
Okay, so you are computer science?
Yeah.
Okay, anyone else computer science? Okay, so everybody computer science, okay, great, so I don't have to explain anything. So that is the reason, it is a really good reason, and it's an excellent reason to take linear algebra, and indeed apply to computer science. So that's make my life easier, my job easier here. So that it will have a certain effect on impact on the way things are presented. And the link to computer science is really not in the title here, really, even though it is certainly algebra is a big part of it, but it is actually data. Okay, so something you're not going to get in calculus is as much as you should. Calculus, you take calculus 1, 2, and 3, and so what's missing there? You study, you learn how to planets move, and what do you not learn? And you don't learn how to deal with data. Okay, and for what's the reason? Anybody has taken calculus 1, 2, anyone? Okay, so calculus. So why it doesn't apply to data? What?
Do you want us to raise our hands, or you want us to?
No, you don't have to raise your hand. Just yeah, speak.
So I mean, data. I mean, so the thing about calculus, it's about like kind of like problem formulation, like how to solve the problem. But data, it doesn't tell you how to interpret the data. It doesn't tell you what the, there's a certain context that you have to have with data to be able to work with it.
Oh, right, but why is it not? It could be data. So if you have taken calculus, why is it not about data? In there, it's usually the examples that put forward for you are physical examples, motion of planets, a thrown ball, and so on. So why not? So why is it? It is kind of data. What's the difference? It is a data. I mean, it's literally numbers of your location in space, or maybe spacecraft. So what is the difference from with you actually doing some computer science and your data? What's the difference between the data of motion through physical space and maybe moving through a space of data?
Calculus is about how things change, and it's normally
and that part you still need. That's part you still need probably whatever you study probably, but but that's not what I'm driving at. There is a difference in the nature of the data, something very important. I'm kind of speaking poorly of calculus a little bit here. Not a calculus as itself, but as a course. So what it does not bring you to, and this course will, is the dimensions. You take calculus 3, anybody has taken calculus 3, that's supposed to be multidimensional calculus, and yet you're pretty much stuck at dimension 3 at best. Maybe even 2. Okay, there is no time. So there's so much time spent on calculus, you never got beyond dimension 3. So you're studying the way the Newton did, study that's such a profound effect on everything. study motion of planets and everything else. Great stuff, but it three-dimensional for you. So what's the dimension of data? 3? Could be more. Well, exactly, but there is no limit to it. The space of data, even if you are just studying, that will come up obviously. Motion, even motion through space, the physical space. 3 numbers is your location. Okay, what else? It could be a lot of other things. For example, if it's an airplane, then there you know what beyond the 3 locations in space, what else you might be recorded. What? Well, time. Everything is happening in time. So it is, even though in physics they do go with space, which makes it 4-dimensional. Okay, but what I'm talking about is for example, the angle of attack. Okay, and so there are actually 3 numbers telling you the orientation of the plane in space, which already 6 numbers. And then you start to collect things. So you decide to record velocity, you start to record, I don't know, temperature outside, temperature inside, the pressure, whatever. And so numbers start to pile up, and you are moving not for physical space only. You could be at the same location, but a different orientation. Okay, so it's already the extra numbers come in, and you cannot see it. And so that's the data, and that's the data, physical data that we know, that we still can see. And then the data, the problem with the data, we cannot see it. Okay, so all the visualizations that we're going to have are really only will be just illustrations. So the data could be 100 dimensional, 100,000 dimensional. So we'll have some examples of that, and to make it clear what I might be talking about is information about customers, for example, name, age, sex, whatever, the preferences about, say if it is any kind of a expert system telling what kind of customer might prefer. So history of purchases, for example, and then it's a bunch of data. What's the dimension? The simple example is the stock market, and there are 10,000 stocks, say, hypothetically. So each of which might change independently, which brings you 10,000 dimensions, literally. So can you see it? You cannot see it. And so linear algebra will apply, but really the biggest part of this course is really this multidimensionality, study of multiple dimensions that you're not gonna typically see in calculus. On the other hand, if you do multidimensionality here, you go to calculus, multidimensional calculus, life will be much easier. Okay, so speaking, having spoken so much about multiple dimensions, the example I start with is lower dimensional. For that purpose, to illustrate as much as possible visually. So we, as long as we can visualize, we should visualize, and then we cannot, then that might be a problem, but really not something that we can overcome. So this is the problem. It is a problem of data. It has nothing to do with calculus or motion, anything like that. And yeah, so we have Kenyan coffee that costs $2 per pound, and Colombian coffee that costs $3 per pound. How much of each do you need to have? Do you need to have 6 pounds of blend with the total cost of $14? Okay. So the problem will go through the whole course. We'll be coming back to it again and again. It is then let's solve it, but without trying too hard to solve it, because in this course and generally in mathematics, no problem has any significant importance. They all together. It only matters where it brings us, and it brings us towards linear algebra. So Okay, so let's solve it little by little. Let's set it up first, and that is, in other words, we're supposed to translate this problem into mathematics. Okay, so if you want to solve it, and then you are trying to solve a practical problem, then you are not. You may, I don't know what you will be doing, but we don't care. We wanted to just to do it the right way, so that the next time we're gonna have maybe different prices, and we can still solve that problem. So we learn something from it. That's how sciences really operate. Okay, so how do we solve it? How we approach it? Once again, if you are thinking in your mind, you're thinking what the answer is supposed to be, and already thinking about the answer, don't. The question is really, where do we start? Well, hold on a second. 2 and 3 are constant. Okay, so those will not, they're not variable.
The attached variables.
Right.
to them.
Okay, so all right, so x and y. What are the x and y?
It would be how many pounds for, X would be how many pounds for the Kenyan coffee, and Y would be how many pounds for the Colombian coffee, and when they're added together, they equal 14.
That's right. So, so once again, one step at a time. One step at a time. We just identify the variables. Okay, there happen to be in in algebra. Usually, you don't even speak of variables. You speak of unknowns. Okay, so which is a productive way. Excuse me. Productive way of thinking about it, but because we are in a slightly different place now, and certainly we're going to rely on that, is that on things that are more mathematical, and so and less algebraic, and that's functions. Okay, and so then we speak of not as much of unknowns, but more about variables. Makes no difference. It's just two different ways of saying the same thing. But nonetheless, so X is the weight of the Kenyan coffee in the blend, not somewhere on the shelf, but we are making a blend. We're imagining that that blend exists with the components that have not been found yet. Okay, so in that sense, they are unknown, and they also variable. If you vary the amount of Kenyan coffee versus the amount of Colombian coffee, that will change the blend, and it will change both the weight as well as the cost. Okay, so then we translate. That's like a little dictionary, and then we are translating our problem now we're using that dictionary into the algebra. Okay, so the total weight is 6. The equation then, number one equation will be x plus y is equal to 6. And the second one will be about the cost. X pounds, $2 each, gives me 2x dollars. For the total cost of the Kenyan coffee, 3y total cost of the Colombian coffee altogether, they're supposed to produce 14. Okay, you can see that the data already has been kind of stratified in the sense that we have the two equations, really simple equations with two unknowns. What is the main difference between these two equations? Really, they're kind of similar. Well, what's the main difference between the two equations? What?
They represent two different requirements for the problem.
Oh, yes, but so two requirements. So what's the difference between the requirements? Well, you can look at the problem again and right, and so which means that the units, right, the units are different. So, right, so the first one is about pounds, and the second one is about dollars. So that's that data and non-homogeneous data. Another thing about calculus is if it's about motion. X and Y, what's the difference between X and Y? There's no difference. It better be no difference, right? So you use inches horizontally or vertically, they should be the same. And here from the very beginning, we already have a situation that is different. But X and Y just happen to be of the same unit. So X and Y, as we're going to plot next, it is in fact the same. So there's no conflict there, but there could be. Okay, so if we were talking about, it is possible to think of non-homogeneous mixtures. For example, somebody decided to measure Kenyan coffee in kilograms. Okay, so then the difference will be what? There will be non-homogeneous data, so meaning that the two different units, and the x and y will have to be, the first equation will have to be rewritten because you have to translate it into the same item, into the same units. But the second equation might remain pretty much the same. Okay, so that would be as an exercise, maybe. So Kenyan coffee, dollars per kilograms per kilogram. Okay, so what's the difference? So rewrite as an exercise. The same problem, the statement of the problem is here somewhere. Wait a minute, where is my, yeah, so sometimes it's just crashes. And some piece of the problem has disappeared. Anyway, so I hope it will come back. But the point is that the statement itself of the problem is pound per dollar per pound. What if the second one of the two is actually dollars per kilogram? The problem still makes sense. Can you rewrite it? And the answer is you could, and so that's a good exercise. And to make the point, once again, the data could be non-homogeneous or homogeneous if you prefer. Okay, so that is it, right? So is there anything else we might need or to make to finish the translation of the problem into mathematics? Once again, we're not trying to solve. We'll see. So these are called linear relations. So you have seen linear functions, presumably, and so we'll review all of that shortly. But linear relations, that's the difference between functions and relations, that one of the variables is not expressed in terms of the other, even though it would be pretty easy to accomplish here. Okay, let's once again, before solving, let's visualize. Okay, so each blend is determined by the pair of points, a pair of numbers x and y. How do we visualize a pair of points, pair of numbers x and y, but as a point, right? So once again, as long as we have only two variables, then we visualize it by creating a pair. That's a crucial step, really. I guess at some point it was a kind of a major breakthrough, I think. From two separate numbers x and y, bring them together in parentheses, and look at them as a whole. So a pair of x and y. X stands for the amount of Kenyan coffee, Y is Colombian coffee, and then, but what is so special about it, we can actually visualize. So what am I talking about here? Here,
Right.
what?
Graphing, right?
Yeah. Can you be more specific?
What is your question?
So a pair x, y, a pair of two numbers x and y, put in the way it is right here. How do we visualize it?
Spreadsheet, maybe.
Well, fair.
Coordinate.
Right, coordinates. The spreadsheet, yeah. So every pair of numbers can be put in a spreadsheet in one column, the other column, but that technically not visualization. It is just the way you handle data, and then you push. I will be doing Excel quite a bit here. You push create a chart, okay, and then it will plot. This has nothing to do with Excel. It's just math. It will plot a point for you with coordinates x and y. So what do we call this system? System x and y's. Plot the points. What?
Or the pair?
It is. No, the whole system. What's the system? There is a word for it. Coordinate plane, the word is Cartesian. And the difference is it might come up again, so let me just show it for you. It is perpendicular. Okay, so that's the XY plane. And then it has, what's the point of it is, Descartes, remember the name? So every point corresponds to two numbers, pair of numbers, X, Y, and every pair of numbers corresponds to a point. Okay, so we gotta, the point is, of course, we're going through this example one by one, things that we have to study in order to understand this problem and then solve the problem and keep solving it. And we already have seen a few, some algebra, linear relations, coordinate system. Incidentally, it's probably what's the difference? What if you can have a system like this? Okay, so that's not a Cartesian system, but as far as the visualization is concerned, you can still use it. So we'll look into that later. But otherwise, so we need to know the Cartesian system. Okay, so and then this is how you plot, and this literally is made with Excel.
For a system to be Cartesian, it has to be.
Yeah, or orthogonal. The axes are orthogonal to each other, which is, as you can see, there really does if you think about it, there is no there is a subtle difference between algebra and geometry. Not the difference, but rather there's a gap between them a little bit. So what's the difference? Algebra, we have been doing algebra so far, and when you speak of angles, that's geometry. So if the problem does not involve the original problem does not involve any geometry, then why do we even care to do it? And so, and we do not at this point, but later on. So that's how mathematics works. Sometimes we remove things that are not important out of consideration to make things as simple as possible. And so the angle between x and y makes no difference. It's just a convenient way to visualize and bring something that you've seen before, and so every time it's perpendicular, but there is no point. If I pick 1, 1 here, and I pick 1, 1 there, so 1, 1 here, 1, 1 there, they just record the location on the plane, and the second one is just as good as the first one. If we ignore geometry and concentrate purely on algebra, the course is called algebra, and it will be probably 90% about algebra. There will be some geometry. Geometry, known as have you heard the words analytic geometry? So as opposed to Euclidean geometry, the one you do in a piece of paper with a ruler, maybe measuring, the difference is the system of coordinates that you can use to do what? Still geometry, meaning measuring distances, measuring angles. So it is inevitably we're going to do that some, but nonetheless, as far as the original problem is concerned, we can entirely put it out of our minds because it requires algebra and nothing else. Okay, so anyway, that's the system we'll review. So that's the introduction. It's just meant to go over one problem and see what is that we're going to need to study in order to understand problem of this kind. So this is I plotted this with Excel. Okay, one point at a time. So how you collect the data from these two might not be just yet clear without expressing one in terms of the other. But let's imagine that we do. So we collect x's and y's that satisfy the equation. Okay, and that produces number one, the red line. The red dots, because I want it is actually a line, but if you do it one at a time with Excel, so that you can actually check. For example, as we can see at the top left, it is 0, 6. Yes, 0 plus 6 is 6. At the bottom here somewhere, it looks like 6, 0. Okay, so in all of these dots, all are verified one point at a time. You plot them one point at a time, and so these are that's the first restriction. The first restriction on the weight is the red line. So every point on a red point satisfies the first equation. The second equation is the green one. Once again, can be verified one point at a time. So once again, we're not doing any algebra. We just understand this about algebra, but we're not doing any formula manipulation, which will be not as important as you think in a course called algebra. But at this point, is pretty much trial and error. So I plug in x and y and can verify whether or not it satisfies the first equation, it satisfies the second. Okay, yeah.
So you can just look at the visualization is your point. You can just graph it and, right, I see.
And you already have ideas, right?
Yeah.
About what the nature of the problem. Or what do you see?
I don't think I fully get though what you mean by the non-Cartesian.
Well, no, that was a point that I was just, it's a side note, the one on the right. But fair enough. You can imagine that what if the plot was not, sorry, the axes were not perpendicular to each other? Would it still possible to produce a visualization? And the answer is yes. Because once again, every point, every XY has a place on the plane and vice versa. So it's just a skewed picture, that's all. You can still visualize it. And some of the things that you can see on this picture would be still visible in that crooked picture. What do you see? Well, what you can discover from what you see about the problem we're looking at?
Relation at the intersection of the two.
Well, you're getting to the solving the problem, which is fair, and we'll get to that in a minute. But what is those red dots? What do they look like if we look at them all together as a whole?
Line.
It is a line. So why the word line so important here?
The limit of the problem.
No, the answer. No. What I meant to say is that's the linear in linear algebra. You've seen the calculus curves. These are not curved, and so that's the easy part of linear algebra. It is there will be no curves. Everything will be straight.
Linear.
Yeah, linear. Okay, so that's the easy part of calculus, and what's the hard part I already explained to you. It's multidimensional. Okay, so and then so it's two straight lines, and so that's why every time we visualize something, they will be always straight. Okay, so calculus does the opposite. The challenge of calculus is what do you do when everything is curved? And so in a way, what calculus is about is finding linear algebra in things that are not linear. Remember the tangent line? Linear, right? So, but you have to find it. So, okay. So every point x, y, and the first line says the first line satisfies the first equation, and the one satisfies the second one. So, all right. So this is for combination of weights x and y to be acceptable, they must satisfy both equations. Then, from the point of view of logic, is then we let's already somebody already suggested the answer. So then the statement over here is for a combination of weights x, y to be acceptable, it must satisfy both of the equations. Okay, so that's a fair statement. Where you can jump ahead and realize that probably the one that really seems to be then there is a point that might be the answer. But let's once again, we're not trying to solve the problem, but rather realize what is that we're dealing with and what we need to study in order to solve problems of this kind. And what comes up is the actual logic. We have to speak of logic as well as in mathematics frequently, but in computer science, well, just as important. In mathematics, only you make a little mistake. In computer science, if your logic is wrong, your program is wrong. So this is what I'm talking about. It's an implication. So I'm rewriting the statement here. So if a pair xy is acceptable, then it satisfies both equations. Okay, so a logical statement, that's what implication is, the condition and then the conclusion. One implies the other. Look familiar? So it's not the same as in programming, but it is the same if. There is no, well, there is if then, except in mathematics you follow up with a statement, and in programming you say do something, right? So if a condition is satisfied, then say add. Your program might say x plus y or something like this, right? So it's a statement. It's not a statement. It is a command to the computer to do something. Verify condition, then do something. Okay, so it is different here, but the logic is similar. So, okay, so that's five both equations, okay? Okay, so implications, so the point being is that we're gonna study a little bit of logic here. Review logic as much as necessary, so a little bit. Okay, restate as an implication each of the following statements. Every square is a rectangle. As an implication right here, following this idea right here. If then every square is a rectangle. Restate as an implication. So in other words, it's if then. If something, then something. So what is it? Yeah, that's right. So if it, whatever it is, that's not important right now. If it is square, it's a rectangle. Okay. So parallel lines don't intersect.
And so are parallel, then they don't intersect.
Right. Right. Yeah. So as you can see, it is something that you cannot really, there is no table or you can memorize a list or something. You just for experience, doing it again and again, you'll get it. But you can see the point that whether it is computing or it is mathematics is very important. Point of view is being very clear which is the condition and which one is the conclusion. Okay, so and then so we would not flip them. Okay, so for example, if I flip my implication right at the on the right, what do I get? If it's a rectangle, it's a square. Okay. Well, what do you say about that?
Changes the meaning of the statement. It changes the logic of the statement.
It changes the logic, yes, but moreover, it is false. So something that used to be true, if you flip it, it's false. It could be false, and so we should be very careful about that, not making that mistake. So we'll be watching out. So also implication, you might see this is in mathematics books. What stands for implications? If you want to write more compact than these sentences, and if you don't want to write if then, which is plain language, but sometimes this is very very convenient abbreviation that you might use. So statement A, statement B, and so a pair XY pair. Remember what we're still talking about? We're still talking about coffee. X and Y is the amounts of in pounds of each of them. And if a pair XY is acceptable, it satisfies both equations, and so the two statements link together in this by this arrow indicating which one is the assumption and which one is the on the right is the conclusion. Okay, so if we try to flip that, might be false. Might be false. We're not saying that it is, but if it satisfies both equations, then a pair XY is acceptable. Okay, so yeah, I literally flipped the arrow, and so that's you can back translate it into English by saying whenever so a pair XY is acceptable whenever it satisfies both equations. So it is everything can have a plain single sentence representation, but we'll be doing both, and so going back and forth actually might clarify what is that we're doing. So the implication is once again a pair XY satisfies both equations, it is acceptable, and that's called the converse. Okay, so the converse. Just a name, and so every implication has the converse, which may or may not be true. So we are just being careful about not saying something that we're not saying. And at this point, we are lucky. Unlike the example with the rectangles, the converse of this, with what we're looking at, is actually still true. So if a pair satisfies both equations, and then it is acceptable, right? Because acceptability of that blend that we have actually is exactly expressed in terms of those two equations. Okay, so okay, converse every square is a rectangle. Already did. Parallel lines don't intersect. Okay, what's the converse of B? Parallel lines don't intersect. We put it as an implication. If two lines are parallel, then they don't intersect. What's the converse?
If they don't intersect, they're parallel.
Right. Okay, is it true or false? Okay, can you explain?
Well, it is true, sorry. I guess I was thinking of a short line, very short, doesn't have to necessarily.
Well, yeah, so lines meaning infinite lines. Yeah, so these geometries, so we speak of infinite lines. So it is actually false indeed, I mean, true indeed, but it is false. It is true on the plane, but. Okay, so, okay, parallel. Don't intersect. Now we do a converse. Two lines don't intersect, they are parallel. Well, you have to know that, what? No? Why not?
Well, they can, they, they can still end, right? You know, they can have endpoints.
No, we speak of infinite lines.
Oh, okay, then no.
No, and it is indeed correct to say that it is false. I'm sorry. It is also true, so both of them are true. But the first one is, the second one is true, is false in three. Parallel lines do not intersect. Two lines don't have to be parallel, right? You see what I'm talking
Oh,
about?
yeah. I see it. Yeah.
Can you explain?
Well, you have like another axis, so it's infinite, it doesn't.
Right, well, yeah, so, no, the axes, but, so as long as they kind of is separated, then direction doesn't matter, so they don't have to parallel. So, the lines do not intersect, even though they're not, these are parallel, these are not parallel, but they don't intersect. In 2D, you cannot do that, so it's pretty much the same thing. Okay, so, all right, okay. So this is another good example when the converse is false, x is equal to 1, it follows, that's directly applies to the algebra. So x is equal to 1 implies that x squared is equal to 1, but if x squared is equal to 1, it does not necessarily imply that x is equal to 1, because I'm sorry, I can't hear. Yeah, I said that the converse of the statement at the bottom over there is false. Why is it false? What?
-1.
-1. Okay, so if you try to go backwards, you skip that's the challenge of solving equations. When you finding one answer is not enough. So going forward is not going to bring you to the right answer. So you have to retrace your steps to make sure that you have found all the solutions. So we have to deal with that too. So all solutions, that's the problem. Of course, if you speak of the there is no problem, so finding one blend is enough probably, but it is possible to imagine, and that's coming up, that there are more than one answer, hypothetically. Okay, so if we know the if, that's when they call the equivalence, and when the statement and its converse both are true, and then we're using double-ended arrow. Okay, so pair satisfies both equations acceptable, and vice versa, and let's finish the problem. Okay, so all right, so if we zoom in, And then visualization is very convenient because then we can zoom in and actually find out how you can guess from zooming in, producing more data. You can guess what's happening with those two lines. But what do we know about, from the geometry about the intersection?
Section is when it satisfies both requirements.
Right, yes. But once again, if we abandon this algebraic approach and think about what we know about geometry, high school geometry on the plane, in fact, what I brought up a minute ago.
The opposite, they're equal, is that way.
Yeah, well, yes, but it doesn't help. So what we just a minute ago, we discussed about intersections, all lines. What was it? Parallel lines don't intersect. Okay, so how does it apply here? Well, they wouldn't intersect if they were parallel.
Yeah, exactly.
Right, so it is relevant here, right? Because we are looking for the intersection and all lines, at least appear to be lines, and then if they were parallel, there would be no solution. Okay, so if we were to say so, and then conversely, if to know that there is a solution, all we need to know for a fact that these two lines are not parallel. So both directions are important. So how do we know there is an answer and they don't somehow cross each other without intersecting? And the answer is we know from geometry that it's impossible if they are not parallel. So all we have to do to demonstrate that there is an answer to the question that we have is to demonstrate that these two lines are not parallel. Okay, so that's one way how we could proceed. And we're not really doing geometry here as much, but nonetheless, here is the solution. It's actually is really simple. You guess the answer, okay, by zooming in. It appears to be 4, 2. Look 4 horizontally, 2 vertically, and then what do you do with 4, 2? Plug it into the original equation, and then yeah, true. You plug in. And at this point, x and y are specific, and therefore you can just see whether or not the statement that's supposed to be true is true, and it is. So 4 plus 2 is 6, and then I plug it into the second equation. 2 times 2 plus 3 times 2 is 14, also true. So that's all it takes. That's all it takes. So we did demonstrate that that for 2 is the blend that we want to be that satisfies the requirements. So are we done? The issue, the issue that I brought up a minute ago. So once again, whoever is making coffee might be totally satisfied, but mathematically speaking, what we might be concerned with. Have we found all the solutions? Just like with x squared is equal to 1, you say x equal to 1, and you get a bad grade because you missed one solution. Okay, so same story here. What if there are more solutions? Okay, so are there any others? So this is a solution, algebraic solution, as you might do. We're not going to be doing it, but this is the kind of a result-oriented attitude towards the problem that we started with. You just start plugging in, substitute, and you arrive to the same answers as 4 and 2. Okay, so this is how, right? Take first equation, solve for y, substitute the second. That way you'll find, you end up with an equation with respect to x, and then solve it. Linear equations. So we're not going to encounter anything complicated. Even quadratic formula will appear only once a while from now. Otherwise, this is the degree of algebra we're dealing with. So no sine, cosine, it will appear later, but not in this context. Exponential functions we don't care about. Polynomials, even they don't really matter in this context. So the solution is very simple by hand. And so you arrive to x equal to 4, and then you substitute back into the first equation, y is equal to 2. Okay, do we need to go over this? So solving a system, so what if it's so simple, why there is a subject such as subject as linear algebra? The answer once again, what if there are many variables rather than just two? So then try to do it by hand. Even three would be quite a lot of work. If you have 100, you need a computer, and so that's we need to be very clear about with computers to explain what is that computer supposed to do. So if we are not sure about it ourselves, it's probably no matter how routine it is, every step is routine, but you have to do it 1 million times, and so that's a perfect place for computers, but you have to understand what's going on to give a command to the computer to correctly, so it would not stumble. So okay, so this is what the implications are. So the first equation implies that y is equal to 6 minus. So once again, this solution is actually, even though it's written in plain language, it's actually there are implications when you solve equations. Every time you have an implication, at least in one direction. So the first equation produces y equals x 6 minus x. The second equation produces something else, or rather item number 1, number 2. There is some structure to the solution, as you can see. So the conclusion of the first step is taking y equals 6 minus x and substitute into the second equation. And then we end up with a new equation, and then we conclude, we take the second step with the equation that we produced, and then solve it once again, and every day a bunch of implications. So this is what I've written here is 4 steps with implications, and so that's what makes it abbreviated, but basically, but entirely what's written there in the paragraph above. Okay, so with you want to be careful, and we do, so that we would not, once again, don't forget about the issue of how we found all of them, and that might be an issue, even though not in the same way as with, say, quadratic equation, which always possibly has two solutions. So, but it is not impossible. So that's why we will be keeping an eye on it. So okay, let's make it more mathematical. This is the system of linear equations. Okay, so that's what it's called. Two relations between the two unknowns or variables x and y, and then you can have 1, you can have 2, you can have 3. And so we already have solved the problem. We visualized it. We spoke of sets on the plane Cartesian system, intersection of those two lines, invoked some geometry. So there is a different approach to data, and that is this. Put the data in arrays, or if the one would say, and mathematically speaking, these will be vectors. Okay, so we already did it. They did it once. X and y, we put them together, and as x comma y, and we spoke of it as a point, but we can also speak of it as a vector. So this is how alternatively the same approach might emerge. So as you can see, even though I could split initially as two equations separate from each other, but actually can split them vertically. So that's the picture in the middle. I'm trying to split it vertically. Okay, so x with x and y with y, left-hand side with and the right-hand side with the right-hand side. So if I take those coefficients, 1, 1, 6 in the first equation, 2, 3, 14 in the second equation, I can collect them on the right in this table, which is called an augmented matrix. Okay, so the matrix itself is this. It is what's in the left-hand side, the coefficients of x and y. Okay, so once again, 1, 1, 2, 3. Okay, and then the numbers on the right-hand side are 6, 14. That's the augmented part. So this is augmented matrix. And this is the matrix. Okay, so then so it's called the matrix, and there are vectors too, and the vectors are the ones that also singled out here. Let me once again show you that we're concentrating on this part. And so you see 1, 2, you see 1, 3, and you see 6, 14. So these are the vectors, and they just happen to be two-dimensional because there are only two variables. So two equations. The dimension is the dimension of the number of variables, the number of equations that we have. So we have two equations, happens to be the same number as the two unknowns, but that's a coincidence. Okay, two equations, two unknowns. It is an ideal situation, which is only true by coincidence. And so we have then two-dimensional vectors because they are two equations. So 1, 2, 1, 3, 6, 16. And then x, y is a different vector entirely. So these are treated to be treated separately, but they're for now they are together. Okay, so then the existence of the intersection point of those two lines tell that it is possible to create such a blend. But so if we forget about that picture and now start thinking in terms of those vectors, then what emerges is, okay, so once again, what emerges is later on. What emerges from here is vector algebra. Vector algebra and matrix algebra. So that what you see in yellow will be reinterpreted as algebra of vectors to begin with, and later on it will be also on the algebra of matrices. But for now, you can see how vector 1, 2 is actually multiplied by x, and then 1, 3 is multiplied by y, and then combined in that manner together, they produce the third vector 6, 14. So that's what vector algebra will be pursuing. Okay, but it appears that before we get there, I actually have next here what I just discussed a minute ago. Let's just elaborate. Is it possible? It is possible to create this blend with that with the settings that we had. What if we tweak the equations a little bit? What if the price of the Colombian coffee is the same as the price of the Kenyan coffee? 2. That's you see the 2 has changed. Colombian coffee 2 per dollar. That's why everything remains the same except for this one. It used to be 3, now it's 2. What's the effect of that? You can guess. What?
Lines are parallel.
The lines are parallel, right? So if you cannot guess, you just plot them and you see. And then we know that if you look parallel, that maybe they are parallel, and in which case they do not intersect, which means that there is no solution. There's such a blend is impossible to create. Okay, so so you can certainly do some algebra to demonstrate that these two lines are indeed parallel, and that's an exercise. But so there are two possibilities now. Is one, blend the original intersection we started with. Now the second case is when the lines are parallel and there is no solution. Okay. What's the third possibility?
Lines be the same
Yes.
and there
Yes.
be infinite solutions.
And there are infinite many solutions. So how do we make them the same? How do you make them the same? So same. So which they're kind of parallel. So what do we do to the equation to make them the same? What do we have to change?
X and Y equals 7.
No, you don't, and there is no x and y. They are unknown. So we're not trying to solve it ahead of time. We just want to make sure that the modify the second equation so that its line is not just parallel to the first line, but also exactly the same line. Yeah, well, you could. So can you give me the answer? Well, yeah. So we could, but if you want to go with 2, it's 2x plus 2y is equal to 12. Right, so it is the same equation, even though it looks slightly different, and as it is often the case in mathematics, so you have two things look the same. If they look different, but might be the same, and then you have to do algebra, sometimes easy, sometimes complicated, to demonstrate that it is the same. And but right now, only we care about that it is the same equation, different equation, but the the set that they produce, the line they produce on the plane is the same. So you cannot say these are technically the same two equations. They're different equations. They might represent different lines, but they do not. How do we know? Either through algebra by dividing by 2 or through just plotting, and then that suggests very quickly that they don't intersect, which means that, well, so the conclusion that there are infinitely many possible blends, okay, but nonetheless, not every blend is still acceptable. See what I'm saying? Instead of having two restrictions, we have one, but it's still a restriction, which means that these are all good. But over here, for example, that's also blend, but that's one is unacceptable. Okay, so a line on the plane, and that line gives you only the good blends, acceptable blends, but the rest of them are still bad. So ideally, the answer is one. So we always hope that there is only one exact answer to the question that we pose. But as you can see, it's not. It is. You can see it is kind of special. Okay, so the generic situation. Think about it. It is part of the linear algebra that we're dealing with. Is generic. If you have one line at random, another line at random, what's the relation between them? What's the generic situation? Well, imagine drop 2 pencils on the table. They're straight, so produce 2 lines. What do you expect them to do with each other? How do they relate to each other? What's the likelihood they're parallel? You throw two pens on the table, and they're just happen to be parallel.
Perfectly parallel.
Well, it is. That's yeah.
Right side parallel.
Yeah. So which means that it's impossible, pretty much. It's not impossible. It's possible, but the likelihood is 0. Because it's such a thin slice of space. When suppose that one line is already there, okay, and I throw the second line on it, and what's the likelihood that it will be exactly parallel to the original one? Well, it will cross it, okay, most likely. So that's why the generic situation is the one we started with that produces one single answer. So that will be part of the course also to distinguish those situations from one. Okay, so examples. These are problems. The type of problems we're dealing with is problems of mixtures. And as you can see, cooking recipes, variables beyond two, weight or count of each ingredient. What the nature of restriction will be the total weight. You want to know how much you have produced, total cost, amount of calories, carbs, fat, and so on. So the relation between the number of variables and the number of restrictions. What's the relation between them? What's the relation between the number of ingredients and number of restrictions that you want to count?
Ingredients, more restrictions.
Maybe not, but it's a trick question. The answer is none. I mean, you look at the recipe, so bunch of nobody counts the end. And it is when they're equal, there's a chance that we are in the generic situation. If they're not equal to, then we are in a special situation, and then there might be no answers, or maybe there will be infinite answers. Okay. So examples: investment portfolio, we have stocks and bonds, and then once again, so thousands of stocks, thousands of bonds, and then you can throw in commodities, whatever, and then the restrictions, total value, okay, in dollars, say proportions of industries that you want to distribute to diversify your portfolio, tax exposure, insurance, whatever, also are imposed on your portfolio frequently, and that's the what we're dealing with is the restrictions of linear. Okay, so you don't square number of calories or anything. You usually add the number of calories from each of them, and then you, depending on what ingredients you're talking about, you multiply the weight times the number of calories per gram, for example, and then you have the total amount of calories in your recipe. Okay, so that it is a linear restriction. Same with carbs, fats. Same with proportions of industries. Once again, they're typically a linear. One more example, insurance balance sheet amounts or rewards, okay, that you might be forced to issue. And then you want to know what's happening, the total value, proportions of various risks, regulations, requirement, and so on. So once again, thousands or millions in each of these two columns, and so that's multidimensionality if you want to deal with data that we are facing. Okay, so restrictions are frequently inequalities rather than equations. Okay, so for example, can you give an example when the restrictions are not equations but inequalities from this list, maybe? The warning over there. So practically all but some of the restrictions. So if you are making a blend of coffee, then obviously you want to have a specific weight, probably have specific weight in mind. But sometimes the amount of restrictions, the restrictions are in that example, in all of these examples, I assume that they are equations. So x plus y is equal to 6, that's the weight, but 2x plus 3y is equal to 14, but what if our interest is not 14, the exact price, but cost, but rather we just don't want it more expensive than $14. Okay, so that would be a fair question to ask. We just do not do it. It's just a matter of keeping in mind that might be slight variations to whatever we're doing. Course is that some equations are replaced with inequalities, or maybe rather than you don't want to have exposure or your portfolio more than 2%. So if it is 0, you don't want 2%. If it's 0, you're fine. So that's how it comes out. Okay, so 10,000 dimensional space intersecting with each other. Okay, so 10,000 dimensional space if you have 10,000 stocks potentially, and so there are lines possibly, maybe these are lines. Actually, let's jump to dimension 3. What do you think if it is dimension 3 and we are dealing with say a coffee with 3 ingredients, 3 variables, we can still visualize it. What does it look like? Restrictions, what does a restriction would look like? X plus y plus z is equal to 6. What does it look like? It's not a line, but what? A plane, right? So you already can imagine how things become more complicated. So you're dealing with intersections of plane and space and how they can intersect. Their possibilities are much more diverse than in the 3-dimensional case. Okay, so multidimensional. So we turn to multidimensional linear algebra eventually. Okay, so we'll review basic things that we just listed, starting with sets, relations, and functions. Okay, so I'll stop here. Thank you. Class dismissed. If you have a question, I see